Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I want to discuss a very interesting topic of a differential equation, that is Cauchy Euler Homogeneous Linear Differential Equations. Cauchy Euler Homogeneous Linear Differential Equation. Cauchy and Euler. This is the combination of two mathematicians who give their more research in mathematics. So he gave a differential equation, Cauchy and Euler, that is known as a homogeneous linear differential equation. So now we want to discuss how we can solve this differential equation. So Cauchy Euler homogeneous linear differential equations. This is the general differential equation of Cauchy Euler homogeneous linear differential equation. So this is the general. How we can say that any differential equation is homogeneous linear differential equation. So here I am writing in a differential equation, general linear differential equation, general linear homogeneous differential equation. So this is n differential coefficient. And here x is independent variable. X is independent variable. Independent variable x. Variable. And y is dependent variable. Dependent on x. Y is dependent variable on x. So here in first term we see that the order of derivative is n. Nth order derivative given in first term. And here independent variable x multiply independent variable, the power of independent variable is equal to the order in first term. And there may be some constant here. An is some constant. X to the power n, x is independent variable, n is the power of independent variable in first term, and multiply with n differential coefficient. Means the power of independent variable is equal to the order of derivative in each term. That is known as a linear homogeneous differential equation. Definition of homogeneous linear differential equation is the power of independent variable is equal to the order of the derivative in each term. If this property verify, a linear differential equation is known as a homogeneous linear differential equation. And this differential equation is given by Cauchy Euler, mathematician, which is very famous mathematician, Cauchy Euler, which is given homogeneous linear differential equation. But the main definition of homogeneous linear differential equation is the power of independent variable equal to the derivative, order of derivative in each term, and multiply with derivative. So here we see in first term the independent variable x, the power of x is n, and here is derivative, that is n order. So power of independent variable and order of derivative both are equal and both are in multiply. Similarly here an minus 1 is some constant, and here x to the power n minus 1. Here x is independent variable and n minus 1 is the power of independent variable, and the order of derivative here n minus 1. In each term, this property verify in each term. Next is, here is x independent variable, power is n minus 2, and here n minus 2 order of derivative. So here the power of independent variable is n minus 2, multiply with derivative whose order is n minus 2. There is a naught is number, and here variable, power of variable is 0, x to the power 0 here. So order is 0, order of this y is 0. So from first term to last term in left hand side, this property verify in each term the power of independent variable is equal to the order of derivative in each term and multiply, then this linear differential equation is known as a Cauchy Euler Homogeneous linear differential equation. And in left hand side there is some function of x, phi x. Phi x is some function of x. So now how we can solve this differential equation? So we will discuss here in detail how we can find solution. So where a0, a1, a2, an are constant in this given differential equation, these constant are multiplied with derivative, and phi x is the function of x is independent variable and y is dependent. Equation 1 is known as a Cauchy Euler's homogeneous linear differential equation of nth order. So main definition, and the power of here, the power of independent variable is equal to the order of derivative in each term. And both are in multiply. This is the definition. This is the definition. The power of independent variable is equal to the order of dependent variable. Order of derivative in each term, and both are in multiply from each term. Each term means first term to last term to left side. Then this linear differential equation is known as a Cauchy Euler homogeneous linear differential equation. We will change equation 1 in linear differential equation of nth order with constant coefficient. Then this equation convert in last equation, which we have already discussed in detail. The homogeneous linear differential equation we change in linear differential equation with constant coefficient. So we will discuss here method how to change Cauchy Euler homogeneous linear differential equation in linear differential equation with constant coefficient. Main motto is to change in homogeneous linear differential equation in linear differential equation of nth order with constant coefficient. To change equation 1 in constant coefficient, then we change in independent variable to x to another independent variable z. Independent variable x. Here to change equation 1 in constant coefficient, then we change a independent variable x to another independent variable z. In our question, x is independent variable, and when we change this equation in constant coefficient, then independent variable is changed. X convert in any other variable, that may be z. So we will discuss here in detail. Following given method is known as a change of given independent variable to another independent variable. Let us consider that following assumptions. When we are taking these assumptions, then we change our given equation, homogeneous Cauchy Euler homogeneous linear differential equation, we can change in linear differential equation with constant coefficient after putting these assumptions. So what are the assumptions? We are giving here proof. So here x equal to e to the power z. We are considering x equal to e to the power z. Taking log on both sides. Here taking log, then z equal to log x. After taking log on both sides. So here x equal to e to the power z. Taking log x equal to log e to the power z. Z comes before this. So log x is equal to z log e. Z log e. Log e is 1. Log e is 1 here. Log e is 1. So log x equal to here z. So we get this result. So here z equal to log x. Differentiating this with respect to x, then dz over dx, we get 1 upon x. And here d dash is d over dz. D dash means differential with respect to z. But in our question, in first equation, we write here d over dx, that is d. D is here d over dx. What d dash is d over dz in other independent variable. D is d differential with respect to x. D dash is differential with respect to z. So now, number 1, how we can change our equation in other variable z. So this procedure is known as a change of independent variable. This is the formula, famous formula, change of independent variable. In our given question, there is x independent variable. How we can change in x to any other independent variable z. So this process is known as a change of independent variable. So here dy dx, in our question is dy dx. So here dy dx, I am writing here dy over dz into dz over dx. Multiply dz and divide by dz here. So we get here dz over dx, this is the value of this. But putting the value of dz over dx is 1 upon x in equation 3. From equation 2, putting value in 3. Then we get dy dx equal to dy dz into 1 upon x. So this equation 4. Now x taking left side, this x taking left side. Yeah, multiply by x here in 4. Multiply by x in 4 on both sides. On both sides. So yeah, x dy dx equal to dy dz. X dy dx equal to dy dz. Dy dz is d dash y. So here we write here formula x dy dx equal to d dash y. That is x dy. X dy equal to d dash y. So we remove this x. In our question, x is multiplied with derivative, first derivative. So we remove the independent variable. Then we get this result. Now 2 point. We can write that d2 by dx2. What is d2 by dx2? d2 by dx2 is dy dx of dy dx. Differentiating with respect to x of dy upon dx. This is the d2 by dx2. So I am writing here dy dx differentiating with respect to x of dy upon dx. This is equation 6. Equation 5, putting value of dy dx. We have already find the value of dy dx in equation 5. Value of dy dx in equation 6. Putting in equation 6 from equation 5, putting value of dy dx in equation 6. Equation 5 is this, dy dx. Dy dx is 1 upon x. 1 upon x dy dz. So here putting in 6, then we get here differentiating 4 with respect to x using product formula. Differentiating 4 with respect to x using product formula. So here is this dy dx dy dz into 1 upon x. This is the from putting equation 4. This is equation 4 here. Equation 4 is this, putting value of from equation 4, putting value of dy dx in equation 6. Okay. Then differentiating with respect to x using product formula. So here differentiating this result, here this u and this v. So we differentiate this uv formula. So d2 by over dx2 d upon dx, differentiating with respect to x d by dx into 1 upon x. This is u, this is v. So we apply here formula this dub. Dub means u differential of v plus v differential of u. We apply here product formula using product formula. So now here this is differentiate, this is equation number 6. This is 7 equation. 7, yes. This is 7. So differentiating here 7 with respect to x. So now here differentiating 1 upon x. dy dx z is constant plus dy dx dy dz 1 upon x is constant. So d2 by dx2 equal to differentiation of 1 upon x here. Differentiation of 1 upon x is minus 1 upon x square. And dy dz is constant plus. Now here inside the bracket, we see that this is function of z here. But we want to be differentiate with respect to x. So here x is changed here. So now multiply dz and dz divide dz. So here interchange dz. So I am writing this d over dz, dy over dz, dz over dx into 1 upon x square. And dz over dx is 1 upon x. So here this equation convert in minus 1 upon x square, dy dz plus d over dz, dy over dz, dz over dx. dz over dx is 1 upon x. So d2 by dx2 minus 1 upon x square, dy over dz plus d over dz, dy dz into dz over dx is 1 upon x. So 1 upon x into 1 upon x. This is 1 upon x square. So minus 1 upon x square dy dz plus here differentiating with respect to z of dy dz. Then we get d2 by over dz2 into 1 upon x square. So now 1 upon x square is common. This plus this minus. So d2 by over dz2 minus dy over dz. This is d2 by over dx2. Multiply here x square. Multiply by x square on both sides. On both sides. Then we get here x square d2 by dx2. This present in our question. And our question convert into this form. So here d square. Here I am writing d2 by dx2. d2 by over dz2 is d dash ka square. And d2 by over dx2, this is d square. This is d dash. Differential with respect to dash z. Differential with respect to z. Differential with respect to x. Differential with respect to x. Differential with respect to z. So this is d dash square y. This is d square y. So now here x square d2 by dx2 equal to d dash is common here. D dash and d dash minus 1 y. This is equation 11. So in our question is x square d2 by dx2 converted this result d dash minus 1. D dash means differentiating with respect to z. I am considering already. And d is d over dx. I am considering already. D and d dash. So now similarly we can prove that in according equation number 5th and 11 we have proved two equations. With the help of these two equations we already proved we can prove this formula. X cube d cube by dx cube equal to we can write d dash minus 1 d dash minus 2 y. This is equation 12. And x cube, this is d cube by equal to d dash minus 1 d dash minus 2 and y. So this is equation number 12. X. Now we have given here three formula. According these three formula we can put next formula. So here first formula is x into dy dx. Here is the power of independent variable is 1 and the order of derivative is 1. So in our question Cauchy Euler homogeneous equation is given term that is x dy dx. X is independent variable. Multiply with first derivative. X to the power 1 here. X to the power 1 multiply with first derivative. That is given in our question. So this question convert into this form dy dz. This is the proof result. X dy dx. X dy dx. This result equal to dy dz. In this is in our question. We convert this question in this form. So in this question is given x independent variable, but after changing this convert into z variable. Okay. So this is the constant coefficient term. This is the homogeneous term. This left side is given homogeneous term, but after change we get constant term, constant coefficient term. So here x square d2 by dx2, this equal to d dash minus 1, y. So left hand side x square, here is 2 power of independent variable x square and multiply with second derivative in our given question. Then this question convert in d dash minus 1 y. This equation 11. Third formula is we have writing similarly d dash minus 1, d dash minus 2, d dash minus 3. Similarly numbers are coming here. So now x cube d cube by dx cube. Here is the 3 power of independent variable, multiply with third derivative. So this is homogeneous term. This is converted constant coefficient. So x cube d cube by x cube d cube third derivative, here x cube equal to d dash minus 1, d dash minus 2 by this is 12. So these basically we are using only these 3 formula, not 4. So these 3 formula, after applying these 3 formula in our given question, then our question convert in linear differential equation with constant coefficient. With the help of equation 5, equation 11 and equation 12, we can change equation 1 in linear differential equation with constant coefficient. Okay, any question given to you, that is second order or third order or fourth order, any order, homogeneous, Cauchy Euler homogeneous equation is given in our question, then after putting these values, we can change the given equation in constant coefficient and the independent variable is changed. In our given question, independent variable is x, but after changing, we get independent variable z, and that equation is known as a linear differential equation with constant coefficient. So here problem 1, I want to solve here problem 1 based on Cauchy Euler homogeneous linear equation, linear differential equation. So this is very important problem, most important problem, very important problem here. Okay. So here x square, we see in our question, this is question. First of all, we discuss the question. Here x square, 2 power of independent variable. So 2 power and order of derivative is 2 here. And both are in multiply. Independent power of 2 of independent variable multiply with second order derivative in first term. Plus second term, there is 4. 4 here x, 4 here 4 and x. This is wrong. 4x dy dx. Here x to the power 1 and first order derivative. X multiply with first order derivative. Plus here 2 and y. Means here is x to the power 0 and d to the power 0 and y. 0 order. X to the power 0. Independent variable have 0 power. Then derivative have also 0 order. So here is 0 order means no order. No order means y there. And right hand side there is some function of x here. This is phi x. Phi x is e to the power x here. So first of all solution, I am writing question 1. Question 1 in equation 1. Here is 4x. So now here d is given here d over dx. Capital D is given in our question d over dx. So equation 1 can be written as, this is x square, this is second derivative. Second derivative is d square y plus 4x. This is first derivative. First derivative is dy. And here 2y equal to e to the power x. This equation 2. Let us consider that following assumptions. We are writing this same x equal to e to the power x, z equal to log x, dz over dx equal to 1 upon x, and d dash is d over dz. This equation 2, 3. So now we write these equations. Already proved this. and this 11, this equation 5, this equation 11 and this 12. We have discussed just with the help of these three equations, equation number 5, equation number 11 and equation number 12, putting these values in equation 1. So here putting from equation 5, 11 and 12 in 1. From equation 5, equation 11 and equation 12, putting in 1. Then we get here is x square d square y, x square d square y in 11 equation, x square d square y d dash minus 1 y. Okay, so I am putting here this value d dash minus 1 y plus 4 x dy from equation 5 is this x d dash y, x dy d dash y, x square d square y d dash minus 1 y. So this value d dash y and plus here 2y equal to e to the power x. E to the power x, x is e to the power z, x is e to the power z. So e to the power z, e to the power z, x is e to the power z here. So here is e to the power z, e to the power z here. So now next solving here, d dash square minus d dash y, here d dash square minus d dash y, d dash square minus d dash y, and here 4d dash plus 4d dash and plus 2 and this y is equal to e to the power z, e to the power z. So now here d dash square and plus 3d dash and plus 2 into y equal to e to the power z. This equation 4. This equation 4. So now there are two solutions of 4. Number 1 is CF. Number 2 is PI. So first finding CF, putting Q is 0, in 4. Then we get here. So here d dash square plus 3d dash and plus 2 into y is equal to 0. This equation 5. Now putting d dash equal to m and removing 5 and removing y from 5, then we get an auxiliary form of 5. D dash equal to putting m and removing y from 5. Then we get here m square plus 3m m plus 2 equal to 0. This is equation 6. Equation 6 is an auxiliary form. Auxiliary form. Solving 6. Solving equation 6. So m square plus 2m plus m plus 2 equal to 0. M is common. M plus 2 plus 1 common. M plus 2 equal to 0. M plus 2 and m plus 1 equal to 0. If m plus 2 equal to 0, this implies that m is minus 2. If m plus 1 equal to 0, then this implies that m equal to minus 2. So here m equal to minus 2 and minus 1. Here roots are different. Roots are different. Different roots. So formula for CF for different roots. For different roots. CF is equal to C1 e to the power m1x plus C2 e to the power m2x. Putting value of m1 and m2. So CF is equal to C1 e to the power minus x. Here is Z. I am writing here Z. Z and here is Z. So here minus 2Z and plus C2 e to the power minus Z. So I am writing here C1 e to the power Z ka whole minus 2 and plus C2 e to the power Z ka whole minus 1. What here e to the power Z is x. We have taken x equal to e to the power Z. So this value putting here, this is complementary function CF. So this value putting here, then we get CF equal to, CF is C1, here is x to the power minus 2 and plus C2 x to the power minus 1. So CF is C1 1 upon x square plus C2 1 upon x. So this is complementary function, complete complementary function. Okay, this is CF. CF of 1. This is CF of 1. This is CF of 1. Now, PI, particular integral, 1 upon d dash square plus 3d dash and plus 2 into q into phi x, phi z, phi dash z function. In our question, phi x function is given, but in our converted equation, function is phi dash z. So now, putting here 1 upon d dash square plus 3d dash and plus 2, here this is e to the power z. Okay, so now here factorizing this, 1 upon d dash plus 2 and into d dash plus 1, e to the power z. So now here this is pi is equal to, now breaking by partial fraction, d dash plus 2 and d dash plus 1 and e to the power z, e to the power and e to the power z. So now here breaking by partial fraction this one. So here d plus 2 minus d minus 1, 1 upon d dash plus 1 and 1 upon d dash plus 2 plus 2 here and plus 1 and this minus. So d dash plus 2, d dash plus 2 and minus d dash minus 1. So here d dash cancel, only 1 here. So numerator is 1 and denominator this. E to the power z this. So now here multiply 1 upon d dash plus 1 into e to the power z minus 1 upon d dash plus 2 e to the power z here. Okay. So this function is phi 1 and this function is phi 2. This is particular integral. This is equation number, this is pi. Now here equation number this 6, auxiliary form equation 6 and factorizing, then putting this formula. This is equation 7 and this equation is this 8 equation. Okay. Now for finding value of phi 1 and phi 2. Now finding value of phi 1 and phi 2 and phi 2 and putting in it, then we get complete pi. So phi 1, what is phi 1? Phi 1 is 1 upon d dash plus 2 plus 1 and e to the power z equal to phi 1. So here is 1 and cross multiply. So d dash, this imply that d dash plus 1 into phi 1 equal to e to the power z. So multiply here d dash phi and plus phi and equal to e to the power z. So here d dash means t over dz. So putting here d phi over dz plus phi equal to e to the power z. This is equation number 9. This is linear differential equation. This is linear differential equation. So now here comparing here dy dz plus py is equal to q. This is equation 10. Comparing p is here 1 and q is here e to the power z. So if taking integrating factor here. Integrating factor here. This is e to the power integral p dz. P is 1, e to the power integral 1 dz. This is e to the power z. This is PIF, integrating factor. E to the power z is integrating factor. So now formula is y into IF equal to integration q into IF and dz this. Not adding constant. Not ma'am 5 minutes. Not adding constant. Not adding constant. So here y is equal to into IF e to the power z integration q e to the power z e to the power z dz. So now solving this, let e to the power z is t. So e to the power z and dz equal to dt. E to the power z t, then e to the power z. So this equal to here e to the power t and into dt. So this result is e to the power t and y is equal to, here is constant adding here. So e to the power t, e to the power z and e to the power z. E to the power z is x and e to the power t. So y equal to e to the power z, z means e to the z equal to e to the power x. This is x here. So this is x and this e to the power t. T is e to the power z. e to the power and e to the power z, and this is x. So this is e to the power x, y x. So y equal to e to the power x upon x. So this is pi. This is value of phi 1. Here is phi, but not y, here is phi. Phi 1. This is phi 1. And this is phi 1. This is also phi 1. So phi 1, value of phi 1 is this. Now, similarly, we can find d dash plus 2 and into phi 2 and equal to e to the power z. So d dash phi 2 minus 2 phi 2 and equal to e to the power z. So here d phi 2 upon dz plus 2 phi 2 and equal to e to the power z. So this equation, this is 10 and this 11 equation. So similarly we can solve this equation. So dy dx and plus py is equal to q. So p is equal to 2 and q equal to here e to the power z. So if integrating factor e to the power integral p dx. So e to the power integral 2 dx dz. So here is z dz. So e to the power here 2z. This is if. So now solution is phi 2 into e to the power 2z equal to integration q e to the power z into e to the power 2z into dz this. So phi 2 into e to the power 2z equal to, now let here e to the power z equal to t. So e to the power z dz equal to dt. So here is e to the power z e to the power t and breaking this e to the power z into e to the power z dz and this equal to e to the power t and this is dt and t dt. Now integrating this by parts, t e to the power t minus 1 e to the power t and this is phi 2 e to the power z is x. This is x square. So phi 2 is here putting t is e to the power z means x, e to the power t, e to the power t, e to the power e to the power t, e to the power x and minus e to the power x. So this is x square. Now phi 2 is x e to the power x is common upon x square and x minus 1. This is equation, this is pi. Okay, this is equation number 13. Now complete CF plus PI. Y is equal to CF and plus PI. So this is equal to CF, C1 1 upon x square plus C2 1 upon x and plus PI. PI is, what is PI there? PI 1 upon this d dash. So here phi 1 minus phi 2. Only phi 1 minus phi 2. What is phi 1? Phi 1 is e to the power x upon x. E to the power x upon x and plus next e to the power x upon x square into x minus 1. So now C1 1 upon x square plus C2 1 upon x plus e to the power x is common upon x square is common. So here is x plus x minus 1. So here answer is C1 1 upon x square plus C2 1 upon x plus e to the power x upon x square and into 2x minus 1. So this is complete PI. Complete solution of 1. Complete solution of 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.